So, welcome to today's lecture. Sorry for the short delay, but no worries. We will catch up and we will get things done today. So let me just arrange the windows a bit. I will try to leave the Menti open through the entire lecture, and you can leave comments and questions there all the time, and I will try to keep track of them while going through the code. Okay, great. So this works. So I will directly switch to the editor, and we will start with oh, this is a lot of movement over there. Okay, well, whatever. Let's start with a simple program. We will write a C program today, and this C program will be very simple. We want to play a bit around with fork and see how fork works. So we will start with the regular suspects, standard IO. We have maybe include, we already know that unistandard age, that's some header that we very often need for POSIX functions. We have our main function, we return 0, and we want to call fork here. And maybe we want to do that one time and then call get character to pause. I use this just to pause the program. Let me just compile this. This was a very quick first program. Okay. Main CPP, doesn't matter. Main. Okay. And now I want to check whether this program is actually running. So I will move this to the background and now run ps-fa grep main. Wow, that's a lot of stuff. Let's maybe rename this. Let's kill this. Let's rename main to slp6.c. Good naming is always a good idea. So let's try that instead. slp6, yes, this works. And G++ should also name the binary in the same way. Okay. Let's try to run this, slp6. Okay, and now let's use again ps-fa grep main grep slp6. Okay, now we see it. Two processes are running here, and we can see their PIDs. Let's just check with less. PID is the second column, so this is the PID. Okay, let's check what we can do with that. We can also use a different command for that. Get PID. Not get PID, that's the syscall. It's called PID of slp6. Let's try that. Oh, there are two PIDs for this program, so it's running twice. Now I want to show you some of the features of the Proc file system on Linux. And in this case, we want to check out the Proc file system for processes. So let's see what we can look up for this process. Again, this is something that the Z shell provides you with just tab completion of the files here. You can check all kinds of different things for this program. I'm interested in the memory mappings of this program. So I want to know which addresses in this program are valid and which are invalid. So let's try to use that with cut proc and then the PID maps. Oh, that's a lot of information. Can we somehow fit this on one screen? I will try to make this a bit smaller. If it's too small, just let me know, then I will increase the size again. Okay. So now we should be able to see everything. And what we can see here is that we have, this is our binary, right? Temp slp6. And you can see over here, wait, can I somehow, I can highlight it this way. You can see here, this is a read-only memory region. Maybe I want to enable the mouse pointer here. Capture cursor. Yeah, now you should be able to see the mouse cursor as well. This is a read-only region. Interesting. This is read-only, but executable as well. Then read-only, read-only, read-write. So this is a writable region. Read-write. Oh, this is the heap. We can see the heap here. Some read-write region which is not specified what it is. Also here. Down there we have here we have shared libraries, and the shared library is similar as regular programs, come with the same regions. So you can see it. You can see that here, then the executable code. Here also a read-only page. Then the executable code. Then another read-only page. There's some data page in the shared library. So it's a pretty similar format as a binary. This is actually a binary. If you would look at this file, this is a regular ELF binary. You can't start it like a binary, but that's just the reason for this is just that you have the main function in a regular binary and not in a shared library. Here's another shared library. So libc, and this is the loader for the operating system that will load our binary, the part that runs in user space in this case, loader and libc. They are shared libraries. Interesting. So here we have the stack, and then some parts for system calls for interaction with the operating system. What I'm interested in is whether the maps in the different processes will be different or the same. Okay, this looked almost identical. Let's see whether anything changes at all. Nothing. Oh, this is interesting. So if we fork a process, we probably still remember this from one of the first lectures. Fork creates an exact copy of a process. And that means that all these addresses stay exactly the same. Interesting. Maybe we can do something with that. I now want to compile this a bit differently because I want to see what this static flag does. Last time I used this to somehow influence the variables. Let me check. There's already a question here, and I will show the Q&A. I guess you can read it. It says, what is the section below the heap? The section below the heap. So this is actually address-wise, this would be above the heap. So we have the lower addresses on the top here because it starts printing at 0 and then goes down to the higher addresses. So it would be the section above the heap. This is very, very far from the heap. I would expect that this part already belongs to this shared library that follows directly afterwards, because you can see that here, this is the first address where the shared library file is mapped. And maybe this is this is 2 pages, right? This is, you can see this is 7000 and here's 9000. Let's do some hex calculations. 1 hex character is 4 bits. This is 4, 8, 12. This means that we have 12 bits. 2 to the 10 is a kilobyte. 2 to the 12 is 2 to the 2 times a kilobyte. That's 4 kilobytes. So 7 to 9 means 7, 8, 9. That's 2 pages, 2 4 kilobyte pages. That means 8 kilobytes. There's some 8 kilobyte space here for the shared library. Maybe this is used to store where the exact method locations are, what the exact method addresses are, for instance. So the heap has quite a bit of space to grow. Yes, absolutely. Should we do the computation? Let's see. So this is, we will not use a calculator for that because calculating with hex numbers is very, very easy. I will show that to you. The only thing that you need to know is 4 bits per hex character. Anything else doesn't really matter. So we have 4, 8, 12, 16, 20, 24, 28, 32. Then we have 36, 40, 44. So 44 is 2 to the 4 times 2 to the 40. 2 to the 40, we know that 2 to the 10 is a kilobyte, 20 megabyte, 30 gigabyte, 40 terabyte. So this would be 2 to the 4 times 1 terabyte. That would be 16 terabytes. And now this is not just a single time 16 terabytes. This would be 5 times 16 terabytes, and we go to 7. So from 5 to 7, that's again 2 digits, right? 5, 6, 7. So you would have roughly, and I'm not counting the numbers down here because they are not that significant in this case. We would have roughly 32 terabytes of physical address space here for the heap to grow. I would agree with you. This is quite a bit of space to grow. Multiple terabytes. I don't have that much memory in my system. Do you know a good cheat sheet for the terminal commands used in this lecture? I don't. And my impression is also, so it took me many years until I felt really comfortable with Linux, until the second, third semester, something like that, or maybe even the fourth semester. I mainly used Windows just because, I don't know, as a teenager, I played around with Linux maybe once, and then realized that no, this doesn't work. It doesn't run any of the games I play, so why would I use it? So I didn't see any advantage of using it. Now for development, of course, this is completely different, and now I use for work, for development, I use only Linux whenever possible. There are some cases where still Windows is required if software is only available on Windows, but it just takes you practice. Like many things that we have in this lecture, it takes you practice. So a cheat sheet, very often it's helpful if you search for a command something that you want to do. If you just search on the internet for bash and then whatever you want to do, bash memory of a process, memory maps of a process, I'm sure you would find this cut proc maps. How can a heap grow that much terabytes if you don't have the space on your PC? This is a bit tricky. Maybe I have to buy more RAM then. You're right. Maybe I have to buy more RAM. But the thing is that in a general case, so if I would really use the memory, it could not grow that much. It would grow until my memory is used up, and then probably things would crash. But of course, this is not entirely true, because depending on how you do that, you might be able to allocate this much heap space. But we still have to figure out how that relates to RAM. What do you think of Temple OS? Will we ever use it? No, certainly not. Okay, so let's continue. We compiled this program, and now we compiled it with static. I want to see what static changes about this binary. And I will, I still have them running in the background. I should terminate them first. Okay, perfect. Let's run them again. I compiled it, I run it. I press Ctrl Z for background. Ctrl Z moves a task into the background, and you can move it back to the foreground with the same key combination, or by typing FG foreground, moving tasks to the foreground. Anyway, I now want to again use the PID of SLP6 command to check the PIDs, and I want to again cut proc 755. This is quite annoying. I don't want to do this every time. So what I can do instead is I can use the backticks here and use PID of SLP6 maps. Oh, this doesn't work because this is bad because it's 2 processes. Yeah, this is unfortunate. You can do different tricks here. In my case, I won't, because I want to check both processes. What could we do? We could do this for P in PID of SLP6. Let's try whether this works. let's script a bit. 4p in PID of SLP6. Do echo p. Done. Ah, this works. Very nice. Now we can say cut, instead of echo, cut proc maps. Ah, very, very nice. But, oh yeah, this is already printing both. So maybe we should have a line echo in here. Echo printing maps, proc maps for PID P, and then cut. Can you still read this? Yeah, I just added this part. I can also make the font larger again if you prefer. And now you can see it here, right? Printing proc maps for PID this and for the other PID. Let's see whether there are any differences. No, this looks completely identical, but the address is changed. Compared to the previous case, the address is changed. Because if you compile the program with static, this is the case on most Linux distributions right now, you don't have address space layout randomization for the addresses down here, for the heap and the data segment and the code segment. So they would be mapped to addresses that are defined in the binary already. Okay, there's another question. Let's check. Will you show us methods how to print how much memory was allocated in a program? I will show you a very simple method for that if you like. Let's do that just right away. I will just comment out this fork call here, and I will use a loop. Okay, let's do this. I should create a global variable for that maybe. How large should the global variable be? Any suggestions? No. 6 is not a very large number. That's a very, very, very small number. (16 bits). Okay, this is already a bigger number. I like this number more. Yeah, 20k. If I write 20k here, it won't compile, of course. Let me show you one thing. Does anyone know this here? 1024 ULL? This is important if you use really, really large numbers. Let's try that. ULL times ULL. So this would be 1024 is 2 to the 10, right? 2 to the 10, 2 to the 20, 2 to the 30. This would be a gigabyte. 1 gigabyte global variable. If it would be a character array, but it's an integer array, so this would be a 4 gigabyte global variable. Should we make it larger? Make it 1 terabyte. Whether it's unsigned long or not doesn't really matter. Even if I have a character here, right? This is 1 terabyte. If I have an integer, this is 4 terabytes. It doesn't really make a difference. It's still about a terabyte, right? The order of magnitude stays the same. This defines whether it is a large variable or not. Even if I use unsigned long, it won't make much of a difference, and it would be 8 terabytes. So creating large global variables, you can also do that with characters if you like. Okay, so let's do that with a character maybe. Okay. And I will just use get character here. Let's run this. Okay. And I will create a second terminal window. So let me just place that somewhere. I have to figure out where, I guess. So let's... this did not work, I think. Oh yeah, this did not work. Now it switched to a different window. This is wrong. So we should switch back to this one. Okay, and I will open a second window to show you. Okay, let's see where this window is. Yeah, this works. So now you can see the system utilization up here. Let me make this a bit smaller. And if I have no clue about how to monitor programs, so htop always is a good start, because it will show you the overall system utilization. So I'm just trying to figure out where to place this, and I will hide the Q&A for a second just to show you how this works. And I have to move a bit down here, otherwise I will knock my head at the window. So let's see. SLP6. We still have to compile it first, right? Oh, this doesn't even work. Oh, this variable is too large. Okay, this is too large. We can't create that. So let's make it a bit smaller. Maybe a gigabyte. Gigabyte works. Okay. So we compiled this. Let's just run this SLP6. Okay. Did you see any change in the up here in the memory usage? I didn't see any change, right? Let's try this again. No change. Nothing. Memory usage state is exactly the same. Let's try something else. I want to try get character, and then I will run a size t loop I equals 0, and I will iterate until, yeah, basically until the end of this array. Oh yeah, I is smaller than this, and then I plus plus. This will take a very long time, right? So let's see. Maybe we can shortcut this a bit. So let's try it like this. So we will go there in 1024 steps. We don't want to do much more. Global array, and there we say I equals, I don't know, 37 times I. That's great. It's a number that, yeah, that doesn't occur in the memory randomly unless we write it there. It should be filled with zeros. I thought this URL just tells the compiler if it should be an unsigned long constant. This tells the compiler that this number that we wrote there, is an unsigned long. Otherwise, it would be automatically casted to an integer, and that would mean that it would be truncated, because integers are much smaller. They don't fit numbers that large. So we are still in this question, how to check how much memory is allocated to a program. And I will show you basically this by using getCharacter, filling the array, and using getCharacter again. So let's run this. Okay, so now please have a look at the memory usage here. No change so far, right? Let's try that again. No change so far. You can also see that in the reserved, you can see here virtual memory, 1000 megabytes. Okay, let's try something. Just before we go to the next step, I want to try something. I want to remove 1024 here and see whether this virtual thing changes. Okay. Okay, so this virtual thing changes. So this virtual thing appears to be related to how much memory I allocate in global variables, but it has nothing to do, and we can see that here in the memory bar, it doesn't have to do anything to do with how much memory our program actually consumes. So this is just some information of like you can imagine it like a plane ticket, right? The program says, ah, yeah, I might use this seat, but unless you show up for the flight, you cannot be sure whether you get the flight, whether you get the seat. So this one is requesting 1025 megabytes, but so far it doesn't have reserved anything. So let's try getCharacter. And what happened? Not really much of a change. So now this changed a bit, reserved changed. So maybe it's not enough to just go through this in steps of 1024. So maybe we have to go through this in more fine-grained steps. Let's try this in very fine-grained steps. +1. Okay, let's try this. Oh yes, actually this, oh, now reserved is at 1024. And you can also see the memory consumption is at 4.08 gigabytes. If I close the program, it's at 0308. Okay, so we can see the memory consumption, both in the overall memory consumption and in this reserved part here, the reserved amount of reserved memory. Okay, let's check whether there were further questions. So let me just make some space for further questions. Show Q&A. So we've done that. So fork made a copy of the main process. It made a copy of the process, whether we call it main or not, doesn't really matter. But it made a copy of this process. In our case, this SLP6 process. Are very large variables used in practice? Yes, they are, but also you allocate this memory often not in a global variable, but via the heap or via mmap. Mmap is also something that we will see in this lecture. Can we focus on the topic and do the unrelevant questions for this topic after that? This is sort of relevant, but I will try to make more progress now. Where was the virtual memory shown? The virtual memory you can see here in this bar, in this tab, virtual memory. This is the virtual memory that is reserved for this process. What would happen now if you again try to reserve more space than you have RAM? Oh, interesting question. This is actually something that I wanted to cover in this lecture anyway, so let's cover that now. So how much memory do I have? 16 gigabytes. Okay. Time to get some more. Yeah, this is not so nice, right? Can we do that? I mean, maybe it doesn't like to have variables that are larger than a gigabyte, but maybe if I have another variable, let's try it like this. So I'm not very good with Vim. It's not my favorite choice of editor, but it's convenient to have the command line and the editor and everything in the same window for streaming. Okay, 8, 9, and this is something where I would say this is super ugly code. Never do that. This is really, really ugly. I really cannot recommend doing that. And I actually think this won't work. Yeah, this won't work because the compiler doesn't support that. I remember something. Let's try to allocate the memory in a different way. Let's try not use a global variable, but we try to use malloc. Well, maybe this works. Void pointer, let's make a character pointer. Global array, yeah, it's not a global array anymore. Let's call it a heap array. Heap array malloc. And malloc, so how does it work? Malloc takes a size t. This is great because the size t can be 64 bits. Okay, so we can allocate a large array with that. Let's try that. Malloc 1024. I should stop this at some point because this is getting very close to what you should do in the practicals. But I will try that like this one with so this is 1 terabyte, 1024 URL, and I hope that this does not kill my system, because otherwise I have to reboot it and everything. So let's see, malloc. Oh yeah, we need to cast this. This is the one part. We need to cast this to a character pointer because it will return a void pointer. We just saw this, and we also need to include the standard lib header, which was also written there in the man page. If we would have taken more care to read it here and here, it was all printed there in the man page. Yeah, I should maybe hide the Q&A while programming. My shell has a lot of sad smileys whenever I press Control-C, and I very often press Control-C just to get rid of whatever I typed there. So I do that very often. And then SLP6, let's see what happens. Okay, so if the stream is gone now, I will be back in 5 minutes, I guess. Oh no, it gives me immediately a segmentation fault. Okay, I know what happened here. Malloc gave me back a 0. Malloc returns 0. This is very odd. Very, very odd. Very, very odd. So maybe this is related to the same problem that we had before, where we couldn't have really, really large variables. So maybe let's try something else here. Maybe let's try to put this in a loop. And yeah, this is great. So I'm also not very good at giving variable names. So I and J, not very good variable names. Don't do that. So I will now allocate 1024 times. Okay. I need some array for my heap array. Heap pointer array with 1024 elements. Okay, and this is a character pointer array, and we say heap pointer array at offset j is this. Okay, and now I want to printf what we got as a pointer. Heap pointer array j. Okay, let's see what happens. I shouldn't be able to. So what are we doing now in this program? We are allocating 1024 times 1 gigabyte. So I'm allocating 1 terabyte of memory with malloc. Let's see whether this works. Okay. Whoa. Okay. No null pointer. There was no null pointer printed ever. All the pointers that came back are valid. Okay. Well, let's try to write to them. Let's try that. Heap pointer, no, let's say heap array, character pointer heap array is the heap pointer array at this offset j. Okay. Also, haven't you noticed I didn't use free? My system should not be running anymore because I didn't use free, right? Very odd, very suspicious things going on here. Who knows whether this is all actually true or whether this is just faked for the stream. You should try that on your own, whether it's actually working. So let's try. I'm now writing into every array. So I'm checking whether so these are 1024 arrays. Each array is 1 gigabyte in size. And I'm checking whether I can write into each of these 1 gigabyte sized arrays. Okay, let's try that. Oh yeah. Okay, this doesn't work. This needs J, okay. Let's run this. This also worked. So there are two possibilities here. Either I have 1 terabyte of memory in my computer, or this is not working as expected. Okay, let's see. Let's try to fill the entire array. Let's go for it. So we fill this entire array. All the arrays that we allocated. The compiler might reduce the malloc space because it is never used for optimization. No, the compiler cannot do that. The compiler cannot do that. Did I overwrite pointers? I store the pointers here in an array, and always the most recent pointer, I copy that one into a local variable, just the pointer. The pointer is nothing more but a number. And then I work with this copy of the pointer. So I'm not overwriting any pointers here. This is actually working on these 1024 different arrays. Okay. Let's try this. Now we are writing into every element of every array, 1024 arrays with each 1 GB of memory. Let's try whether this works. No problem. It's good to ask because others might have wondered the same thing. So I will continue. And what happens? Oh, seg fault. Seg fault. But wait a second. This should print. Wait, where did I have the printf? The printf comes at the beginning. So the printf came at the beginning, and this never printed any other number. So this is a bit odd. Let's make sure that this is really flushed. Let's use fflush standard out so that we are sure that this number was really printed. Oh yeah, this is wrong. We have a bug here. We don't want to iterate through 1 TB. Otherwise, we run out of this array. So let's try this again. Without a bug now, I wrote out of bounds. Of course, this will crash. Let's try this again. Okay, first array, second array, third array. And you can see the memory filling up, and the stream might become a bit laggy at some point. So we are filling up the memory. You can see how it fills up the memory. You can see that both in virtual and reserved, this is filling up the memory. And you would say at some point we will get a null pointer back, right? Because okay, so now it crashed. Why didn't we get a null pointer back? It should have printed a null pointer if it goes out of memory. Instead, we got a seg fault. Interesting. This is not behaving as we learned, right? So we learned something different. We learned that we always have to check whether malloc returns null, because it might not. But we printed it here, whether it returns null. It never returned null. It definitely never returned null. So this is very interesting. And I will go back to the Q&A with that. Let's make some space for the questions. And what would happen now if you, again, try to reserve much more space than you have RAM? You just saw it. I get a seg fault. Very unfortunate. Why does your shell end lines with a sad smiley? Every time I get an error return, or that I get, for instance, if I press Ctrl+C, that would also create an error signal, and then I get a sad smiley if I get an error back from a program. Isn't dynamic memory automatically released once the program exits? That is a very good intuition. I think you should keep that intuition. If there are any more questions, I see some question marks are left over here. If there are any more questions, just ask at any point. But this goes a bit into the part of the exercise where you should also figure things out on your own. Yeah, I see a lot of cat smileys also there. The cat is actually sleeping right next to me, but I don't want to wake her up. Maybe she wants to enter the stream at a later point. So let's continue. We have still a bit more than half an hour left, so we can still do continue with the part with fork. Fork, get character. Yeah. What do we do with this code? I don't know. I don't need it anymore. Gone it is. Perfect. Yeah, I don't like comments. Code without good code shouldn't have comments. That doesn't mean that code without comments is good code, but good code without comments. Good code is without comments, but not the other way around. Okay. So we want to check the following things. So we just saw these proc maps. Could we, as a user programmer, figure out whether an address is valid or not? Let's try that. I will try that in a very simple example. So I will write, so I don't need the fork for now. I will use that later. Volatile size t pointer. I'm using volatile here. So to tell the compiler to not optimize this out, because the compiler might realize that I'm writing code that doesn't make a lot of sense. So I'm initializing this pointer to 0. This is the null pointer. And I will now dereference it and check what happens. Any ideas what will happen? Any guesses? Yeah, of course, the segmentation fault. I mean, what else would you expect? Yeah, of course. So this code doesn't look very useful. But the thing is, let's imagine we use fork and use this dereference in a child process. What happens then? So let's try that. So we create a child process, PID fork. Okay, if PID equals 0, then we are the child, and the child should do the dirty work for us. Address, and then we will print a message. So we will print a message, just making a new line here so that we have nice output. The address P is valid. If we reach this code, then the address is valid. Okay, perfect. So then what happens in the else case? The else case is the parent case, right? And here we will check for the return value of this child. And how do we do that? With a command called waitPID. If I wouldn't know how to do that, I would start with the forkman page. And here I check how to wait for a child. It has some information on C also, but also you can just Google for waiting for child process. You will find waitPID. waitPID is the syscall to use here. We need to include two things, systypes and syswait, and we use this waitPID call. Let's quickly check what it does. We should always read the documentation, but of course it can be a bit boring at times to read the documentation. If a child has already changed state, it calls return immediately. Here, wait and waitPID. The waitPID system call suspends execution of the calling thread. Very important, calling thread. So if you have a multi-threaded program, you can let one thread wait for another process to die until a child specified by PID argument has changed state. And this in many cases means the process died. But there can also be other state changes that we can look out for. By default, waitPID waits only for terminated children, but this behavior is modifiable via options. Yeah, okay, so we like the default behavior here, and we just want to wait for any child. Yeah, sounds good. So we just want to wait for any child. Wait for any child. And the defaults sound also, for options sound also good. W status, maybe we still have to figure out what this is. I haven't read anything about this one yet. Here. Wait is equivalent to this. Okay, so this uses this status. Let's search for W status. Okay. What does it do? W status. If W status is not null, then W if exited returns true if the child terminated normally. That is by calling exit or exit. V exit or W exit status. W if signaled returns true if the child process was terminated by a signal. Oh, this is interesting. We will use this. If the process was terminated by a signal, I'm thinking of a seg fault here. So we will use this as well. So let's copy this over into our code. We can use this directly. Just copy it here. Okay. Very nice. So we just use the waitPID system call. We want to wait for any PID, and there it said -1. We want to get some return value. And then we don't care about the options. waitPID. This is basically what we need here. waitPID So now we can wait for any child to terminate. And we only have one child in this example, so this should be good. Now we will check is this W if signaled, whether the process was terminated with a seg fault. And if so, we can say, well, address P is invalid. And here, what I really like to do sometimes, but I will copy this from somewhere. I like these color codes. You can look up color codes also. It's something you can easily find on the internet. Okay, let me just copy that here. So this is a color code to basically yeah, make the output a bit more beautiful. Let's see. A flush. So we want to make sure that everything is printed. And yeah, let's see what this does. Okay. And oh, perfect. This prints address nil. Okay, this is the printf with %p prints nil instead of 0. Yeah, this works. Oh, we need to write a loop. Let's do that in loop. While 1. Okay, this doesn't sound good, right? I mean, what we are doing here is we are provoking segmentation faults to then tell whether an address is valid or not. So we will get a lot of segmentation faults with that. Maybe let's start very, very slow. Sleep 1. Let's compile this. Okay. Okay. Should this continue? Okay, this doesn't seem to work really. Let's also check. Okay, no other processes running anymore. But this is really, really, really slow. Why is it so slow? Address invalid, a flush, sleep 1. Oh, let's try something faster. Let's try usleep 100 or 1000. 1000 should be 1 second, right? 100 should be 100 millisecond, right? Am I right? Or let's check the documentation. Usleep says microseconds. Okay, so 1000 would be 1 millisecond. That's fine. 1 millisecond is better. 1 millisecond. Okay. So let's the address here, the address. We need to increase the address because otherwise we are always probing the null pointer. That's not very useful. So we want to increase this by the so-called page size, which is 4 kilobytes on x86, the smallest page size. Anything below that will not really change. So you can only make addresses valid or invalid in blocks of 4 kilobytes. So let's see how that works. But you can also play around with that. You can experimentally, empirically determine what the page size is just by checking when the memory increases, at which byte offset it increases. Okay, let's try. Oh, and you can see every printed message here. Every time we print a new message, this is a new seg fault. This is a lot of seg faults. Oh, there were some valid addresses here. Very nice. This is, you can see this is the same range. Let me just put this into background and then PID of SLP6. Okay, I have several running. That's, yeah. Let's just take any of these proc maps. And you can see that, yes, this is exactly the addresses that should be printed as valid. B8 is valid, and then it prints a lot of invalid. B8 is valid. Let me go to the start of this region. So it starts at, 3F8 is invalid, and then 4, 0, 0, and then another 3 zeros. This is the first valid address. So this is also the first valid address here. And then at the end, it might, so these might be memory regions that are reserved, but they might not be allocated because no one ever accessed them so far. But I'm also not sure. Ah, yeah, I know what I did wrong. If you take a look at the code here, you might have seen it. I'm using a size t pointer here. I should use a character pointer because otherwise plus 4096 pointer arithmetics would be multiplied by size t. So I introduced a bug there. Let's try whether it works better now. Okay. Yeah, and you can also see some Python process here. This is the apport mechanism, which reports all these programs to be segfaulting. And it's basically reporting all the time, oh no, another program segfaulted, another program segfaulted. So yeah, okay, so this is not so nice. Also, I'm wondering, I mean, this is already a lot of segfaults per second. How far can we get? Let's go for this. Only 10 microseconds left between every segfault. Okay, so the limit is clearly not the uSleep here anymore, but the fork and the segfaulting will take time, so this will be slow. But as you can see, it works. I can have a lot of segfaults per second, and it doesn't do anything. It doesn't hurt my system. My system is still very well usable. Wait, let me show this window again. I didn't realize it. So you can see the Python apport process here, reporting all the time the processes that are dying as, oh, this is not functioning anymore. Your application stopped working. But you can see that my system is not really exhausted by that, right? This is, yeah, it's still not a lot of utilization. So we had much worse cases there when we tried to have something massively parallelized, and we don't have that here. Okay, interesting. I can just let this run, I hope. I mean, maybe my system will die at some point, but hopefully not. And I will answer a few questions in the meantime. Let me just try whether I can I make some space here? Yeah, now I have some space for questions. And let me also remove this part again. So now we have time for question. Okay, one person was unhappy with something that I said. Maybe I'm very sorry about that, but maybe we can figure it out. So if you have any questions, I would be very happy to clarify and yeah, make things as clear as possible. Why do we get a segfault and not a null pointer? Because malloc cannot know that things will go wrong. Malloc does not know that. You can imagine malloc pretty much like a mechanism where you reserve a ticket, a plane ticket. And if you reserve a plane ticket, that doesn't mean that you get a seat in a plane. It means that the airline will likely give you a seat in a plane. But if something goes wrong, they won't. If something goes wrong, they will give the seat to someone else because they do this overbooking. So maybe we have similar concepts also here, but I leave that for you to figure out for the exercises. How can getting more memory than RAM bring you a segmentation fault? Does RAM contain memory that shouldn't be accessed? No, the situation is a bit more complex. The thing is, you have to distinguish between yeah, similar as with the plane ticket. The plane ticket you have and the seat that you have. So with a plane ticket, it doesn't mean that you actually get the seat in the plane. What exactly are we trying to prove by validating addresses? I'm trying to check which addresses are valid and which are not. And I could write a program now which checks before dereferencing any address, checks is the address valid or not. And if it is not, it will print an error message instead and say, oh, there was an error. This address is not valid. please search for the error. Here was what we tried to do, so you don't get a seg fault, but you can have much nicer error handling. But you can also do that in a more beautiful way with signal handling. What are we trying to prove here? We are trying to prove that segmentation faults are nothing to be afraid of. We are trying to prove that the addresses that we allocate, we saw multiple indicators for that now. The addresses that we allocate are not really the addresses. We don't get these addresses immediately. The operating system promises us that we get these addresses, but there's some mechanism in there that allows us to make addresses valid or invalid, and allows us to to have more addresses and allocate more memory than is actually technically possible. So the operating system builds up some illusion here, and we still have to understand how this works. And this will take time, and we will only fully understand how this works in follow-up lectures, not even in this lecture. Why are the addresses after 0 also invalid? Because imagine you have a case where you want to dereference a pointer, and the addresses, the pointer address is used in an array, in code where it's accessed as an array. So you access some offset to the null pointer. Let's say you access a large array, and the base pointer is a null pointer, and the base address is the null pointer, and you access at offset 1 million. So you would have, if it's an integer array, 0 plus 1 million times 4 bytes for the integer. So I think the cat wants out though. Yeah, the cat definitely wants out. So unfortunately the cat is gone now. So you would not access offset 0, but you would access offset 4 times 1 million, which is 4 megabytes. So it would be wise to leave even the first 4 megabytes free. And following the same logic, it makes sense to leave the first few hundreds of megabytes free, so that if you have a large array and an access to a null pointer, you would still catch this problem. Otherwise, your null pointer dereference might go completely unnoticed and just access data from some unrelated other memory location. Why are the... Oh, I think I marked the wrong question as answered. Sorry. Which question was that? Oh no, the question was duplicate. Okay, so we had the same question 2 times actually. So this one was there twice. Why is the output of the address updating and not printing a new one in a new line? I actually implemented this intentionally this way. So if I remove this code here, \033, and then what is it called? And sort of one of these braces, like a eckige Klammer, 2K, and then \R for rewind. If you remove this and run this again, then it prints, of course, new messages all the time. But with that, you can make sure that it's always using the same line, which can be quite convenient if you don't want to spam the terminal with output. Okay, what is assignment 3 all about? It's about understanding that some things are off. Some things that you learned so far in your studying program, in your computer science studies, were explanations that were good for you at the time, but they were wrong. It's similar as it can be a good idea to tell children that there is something like Santa Claus, right? Because that makes many explanations easier, like where do the presents come from? Why is the present this year not as exciting as the one from last year? Why is or many other things. It makes sense to give some abstraction, some cover-up story to make things easy to understand. And you have been told these stories, and now it's time to realize what the truth actually is. And that is pointers work a bit differently than you thought. So this is what assignment 3 is all about. How does memory work? Yep, my stream just stopped. I think it's back now, if you can. And then you might have to press the resync button down there. If you press the live button, you are back live. So I'm not entirely sure where it stopped, but let me just quickly repeat. Assignment 3 is about understanding what what you have been taught that is not true, just for reasons of simplifying things, just of making things more easy to comprehend at first. For instance, the entire concept around pointers, there's much more behind it than you have learned so far. And in this assignment, in assignment 3, we will observe that there are things that cannot be explained with the explanations that we have gotten so far in previous lectures. So basically it motivates why we need to think about what the actual explanation could be. And this thought process, this is something that I've experienced over many years. This thought process of really understanding how pointers really work and how virtual memory and memory in general, how it really works. This takes a long time. So it makes a lot of sense to start thinking about that now, and you will gain a full understanding of it later on in operating systems. So I thought I already marked that as answered. Guts, yes, yeah. I think people like the guts very much. So allocating X memory but never using it will never be a problem, even if X is very large. We have seen a case where this was a problem, right? We tried to allocate 1 terabyte of memory at once, both with a global variable and with malloc, and in both cases it did not work. So this was, yeah, you could say this was a problem. So if X is very large, it can be a problem, but it's not the problem that you were thinking it is. It's not the thing that you see whether the system or the process or anything goes out of memory. It's a different effect. So it was not entirely the truth that we learned here in the past. Somehow this seems like exception handling in C. Is this comparable? No, we are creating a new process. If we look back at the code, we are not using exception handling here. And we are also not transferring control like with an exception. You can see that here the fork. Here you perform here you run the code that gets the segmentation fault, and this is not caught anywhere. This is the segmentation fault really is executed, and the operating system then sees, oh, some program crashed. On Windows you might get these notifications, SLP6 stopped working. So this is really crashing programs. It's not exception handling. Signals might be comparable to exception handling. Can we assume that reserved space is the same as virtual memory? So let me check. If I go back to the to this htop thing here, where do I have it? Looking at the reserved space is the same as virtual memory. No, one bar up here. If you look this up, one is virtual, one is reserved. They are not the same. So yeah, they are definitely not the same, these two columns. Could you explain mmap and its interaction with the OS in detail? We will do that, but I think we will not do that today anymore because there are still a lot of questions and we are already almost at the end of the lecture. And I think I covered everything that we need for assignment 3 mainly. So I think we are good on the timeline. But I will explain it in the next lecture. We will use mmap. We will have shared memory between processes and try to sorry, I just lost it. Try to communicate from one process to another. Okay. Can you give an example of the cover-up story and correct it? Well, there are many cover-up stories. One, for instance, is Santa Claus, and you tell it to children so that you don't have to explain them something. Other cover-up stories might be, I don't know. I guess people who already had children know more of these cover-up stories. But I guess there are a lot of cover-up stories. Maybe you can share the best cover-up stories from your childhood in the YouTube chat. I guess that would be a lot of fun to hear. The best cover-up stories. I just read one a few days ago somewhere on the internet where someone told the child that so the child was afraid of ghosts, and the mother told the child that that the child can vacuum the ghosts away, and basically the child was then vacuuming the entire flat. Yeah, a very nice cover-up story to get the child to do some work, although the child thinks it has a completely different meaning. Cover-up stories are there everywhere. Regarding programming. There's this very nice cover-up story. I always explained this when I was still a tutor in the introductory C and C++ programming classes. I explained to my students that pointers are nothing more but numbers. You can consider the entire memory of the system, the RAM, you can consider this a large array, and pointers are basically an index into this array. So they are nothing but a number, and you can do computations with this number. Pointer arithmetic. It's just a computation of an index within this array. Totally easy to imagine. This is complete, well, technically, for many things, the explanation will work. And I think it's important to first get an understanding of this level. But of course, this is complete nonsense. It's a cover-up story, and a pointer, you can consider it an index, but if you learn what it actually is, you will be surprised that it's not an index. At least not directly. Could you explain the example briefly? What happened exactly? I'm a bit slow. So you want to see the example again? Let's do that, of course. And you can you can't see the Q&A anymore. So yeah. So let's go through this again. So what do? We have our null pointer here, address, character pointer, null pointer. We have a while loop. So this code runs forever, and this will never terminate. Because I will run from address 0, I want to run until the highest address, so this would be 2 to the 64. I'm running there in steps of 4096. This is 4 times 1 kilobyte, 4 times 1024. So it's 2 times 2 to the 10. So it's 2 to the 12. So we are iterating from 0 to 2 to the 64 in steps of 2 to the 12. So that would be 2 to the 52 steps. We will get very old before this would finish. So this is a while one loop, because this will never finish anyway. We've been told that a pointer is a variable that contains the address of a value and has its own address. Not that they are just numbers. Well, but that's the same. A pointer is a variable that contains the address of a value. Not necessarily. A pointer doesn't have to point to anything. If it's a null pointer, it's still a number. It's still a variable that contains an address, the null pointer, a number, but it doesn't point to a value. But of course, a pointer is a number. If you store a number in memory, it will need memory for that, and you will have an address where this number is stored. So yes, the pointer will also consume memory itself. So let's continue going through this example. We have this while loop. We have the fork here. We want to create a forked process, a child process, so that we can, let me just switch to this window that I can also properly see it. We have the fork here. We create a child process so that this child process will get the seg faults, but not we. We as a parent say, oh, the child should do the dirty work. We don't want to crash. The child can crash for us. That's better. So the child will then dereference whatever address we have here in the first run, the null pointer, and then print this message if the address was valid. If it was not valid, it will already crash in this line, and this printf will never be reached. So no message will be printed. Then in the parent, we create some space for a return value. We use wait PID, wait for any child, store the return value in this return value variable. We just take the default options. We check whether the return value tells us that this program crashed. If it crashed, we print the message address P is invalid, and we flush standard out. We have to do that so that we are sure that even if there's no new line, the characters are actually shown on the terminal. If we don't add the flush, they might not be shown on the terminal. Then we perform a usleep just to slow down the program a bit, but we wouldn't have to do that. Then we have the address here, which we increment by 4 kilobytes, so that upon the next run, we try the next address. So we iterate through the entire address space, starting at address null, continuing at address 4 kilobytes, 8 kilobytes, 12 kilobytes, 16 kilobytes, and so on, and checking, is this address valid? And if it's valid, we print a message. If it's not valid, we print a message that it's not valid. And this is an example where we use fork and where we also learn something about how addresses work. We can just try to access them, and somehow it works. Even if all these addresses are invalid, we can still figure out that they are invalid. Of course, we could also just use proc maps, but this is also pretty cool because we can do this with our own C code. Let's continue with the next question. How many questions? Oh, let me just close this again. How many questions are there in total in the questionnaire for assignment 3? And do we need a program for each question to help with our thinking? So what we do have as a requirement is you need programs for each question. If you run into the situation that we suspect that you might have plagiarized your solution from somewhere, if you then don't hand in the programs that you wrote on your own, then you have nothing to prove that you did this on your own. So this is it would be helpful for you if you submit these programs into the Git repository in these cases. Every year we have something like maybe 10 to 20 cases of suspected plagiarism for assignment 3. In some years it's more, in some years, so we had cases where it was like even 30, 40, 50 students. Sometimes you see, so we have a special algorithm to detect these cases of plagiarism, and you can really see the rings of students that exchanged their answers there. So yeah, it helps you to defend that you have done it yourself. 30 questions, yeah, I was thinking something like 20 to 30. What if we supplied code for only the more difficult questions? Totally fine, totally fine. If you can make a convincing case that you did it on your own, if you can convince us that you did it on your own, we will of course give you the points. The thing is, we in the end have to sign a document which says you have done this on your own. The document where it has your grade, this says you have reached the learning goal and you have done this on your own and according to all the statutes and plagiarism guidelines that we have at TU Graz. And I can only sign this if I'm really convinced that this is true. So you will have to make a convincing case if such a suspicion comes up. Does fork clone the process at the current state? Will it start main from the beginning or continue at the point of fork? It continues exactly at the point of fork. We can also try to look at that in code. So we will do that here. Let's just call exit here. I just want to add some code here. Fork printf before. It's easy to try out. Things like that I can always recommend to just try things out and see what happens. Before and after, and in between we have a fork. Let's try what happens. We compile this, we run this. 1 time before, 2 times after. So this is exactly what we expect. It continues at the point of the fork. Okay. This is a lot of information and a lot of cliffhangers. Do we have to worry? No. Assignment 3 will give you a lot of questions, I guess, as you explore how programs behave, but it will also give you answers. And most importantly, it will give you a better understanding of how the system behaves. Things like malloc, I bet that for many students in this stream, there were some news today in the lecture where they thought like, okay, I know how malloc works, and now they realized, okay, maybe it's not how malloc works, or maybe this is not how variables or addresses work. So it already helps you getting a better understanding of how the system actually works. And we are here in system level programming. We need to understand a bit of how the system interacts with us as a user programmer. We don't need to implement the system part, so we're not in operating systems. In operating systems, you will implement all of this. So it's good to just see this from the other side first, from the user side. When will we have to do the questionnaire A3? There is a deadline in the on the website. We have a deadline for A3 where it says until when the questionnaire has to be done. And the discussion rounds for A3 are in the week after that. What can we understand under the large global variable in assignment 3? I think we have seen a large global variable today. We have seen that an unsigned long is not a large variable. It's not very large. You wouldn't be able to see that in the overall memory consumption in the system. A large global variable is a variable where you can see the difference in the global memory consumption of the system. Sorry, I just cancelled the wrong question, I think. There was one more question. Is A3 only questions? Yes, this and the discussion round. Can or should we upload our programs to the Git repository anyway, or just if there's suspected plagiarism? Anyway, so if you didn't commit code at the point of the deadline, and then later on say, oh, but I did it on my own, and say, oh, but here's the code, then we don't know whether you wrote it afterwards or yeah. So it has to be in the repository at the point of submission, otherwise it doesn't count. What will happen at the discussion round of assignment 3? We will, and before that, maybe also this question here, do we have to tag also? Yes, you have to tag assignment 3 You have to tag the code that you use, that you submit into the repository. What will happen at the design discussion of assignment 3? We will sit together in the Discord and discuss all the questions. So we will have a chat and talk like what could be a possible explanation, how can we get a better intuition of the system here. Yeah, it will just be a chat where we talk about the observations that we made and what this tells us about the system. Yeah. Of course, we expect you to come there a bit prepared and also to contribute to the discussion. And if you contribute to the discussion, then you will also get, you will get more points. You will get 0 points if you don't contribute anything to the discussion, and you will get more points if you contribute a sufficient amount to the discussion. But also the tutors might ask you to not say too much, so everyone should say approximately 2 important things during the design discussion, and then they will get the maximum number of points, maybe a third, and then they will get the maximum number of points on this discussion round. Would a character array with 1024 elements count as a large variable? This would be 1 kilobyte. Would I see 1 kilobyte of memory consumption change in my overall system? This only shows things in gigabyte. I can't see kilobyte in this, so I can show you this htop again. Would I see 1 kilobyte difference here in this memory line? No, I wouldn't see 1 kilobyte difference. So this is not a large variable. I need to be able to see a difference in the overall system memory usage. So we basically don't need to make code segments if we can explain the answer in the discussion. The problem is if we suspect that you copied the answers from somewhere and you don't have code in your repository, then we will count this as you copied the answers from somewhere. That's how it works. So if you decide this will certainly not happen, because I will certainly not have the same answers as anyone else, and I'm absolutely sure of that, sure, go for the risk. Why not? No risk, no fun, I guess. But in general, I would say if you write code for one question, then you should also submit the code into the repository. We don't judge or grade how beautiful the code is. It can be the most ugly code that you have ever written, totally fine. No one will ever see it except for the tutors, and they will only look at that if there's already a suspected case of plagiarism. What is a sufficient amount of contribution in the discussion? So for instance, if you made an observation and you contribute to the discussion, like what the observation was, maybe you have figured out some detail that someone else didn't figure out, you can contribute this to the discussion, and this would be a meaningful contribution. And I expect something like 2 or 3 times saying something like that, contributing something like that, that no one else has brought up. An interesting observation. Let me continue at the start, because it always moves down with the questions and not with the upvotes. What is a pointer? Yeah, that's a good question. So I won't fully answer this question, because then I would have to get out at least 2 lectures of the operating systems lecture, so we can't cover this entirely here. What is a pointer? Maybe in assignment 3, come up with a good explanation of what a pointer is. This could be a meaningful contribution to a design discussion, the understanding of what a pointer is. You will see that it's not directly a question in a questionnaire, but for several questions it's relevant to understand how pointers behave. And for that, I'm sure that you can figure out some interesting observations, figure out some interesting explanations. How many questions are there in total in the questionnaire for assignment 3? there is, I think we already had that in chat earlier, it's 30, I think. Yeah, I think we already answered this question also. How about you count yourself? I would expect to have programs for almost all of the questions, but many of the questions you can combine into the same program. So I would write one program where I get a large global variable, heap variable, m-mapped shared memory variable, local variable, static variable, and just run all the code on these variable types, and then you will get all the answers for the different questions. Try to fill them with memory, try to access all the elements, try to allocate a lot of memory but not access them, try to initialize them from the start, and then you will already have, with a single program, answered something like 10 questions. Can you please get Hexe back on the stream? I think I can't. No, she's not there, so I can't get her back into the stream. What are the practical usage examples of fork? Practical usage is, for instance, in a server setting, you have a server application. You don't want the PHP script or the PHP interpreter, which might be super buggy, to crash your entire web server. So you fork the process for every request. And then if you have a request that crashes the server, it will only crash this instance. And yes, then this instance will not respond to the request that the user sent to the server, but the rest of the server would be entirely unaffected and could still serve requests in the same way. It seems like a lot of overhead. It's actually not a lot of overhead. Fork is actually quite, yeah, it's actually quite fast. And of course, modern web servers don't use fork directly anymore in most cases, but they would have a pool of processes and distribute the work into this pool of processes. So they would not always create a new process, but use a pool of processes. But you can still use fork, and that's still used for fault isolation. As I said, if you run untrusted code, you would fork so that you still keep control of whether the program continues to run or not. And the untrusted code might crash totally fine. Another example would be combining fork with exec, because with exec you can replace the memory contents of a process with a new binary. So you would first call fork and then exec, and that's like running a new process. Where's the questionnaire for A3 in the test system? Yes, that's correct, in the test system. What if we have, what I've answered all answers wrong in the questionnaire? That would be very unfortunate, because that would also mean 0 points. If all answers are absolutely wrong, then this would also be 0 points, regardless of the discussion round, sorry. Couldn't your example with the web server be done with threads too? If you get a segmentation fault in a thread, then the application, I would expect the entire application to terminate. It depends a bit on the system, but I would also, you cannot be sure whether the segmentation fault, I mean, the segmentation fault can occur, but also you could have random memory corruption if you access, for instance, uninitialized variables. It could be pointers that point to a memory of another thread. So this wouldn't work with threads because a fault would not be isolated into another process. The process might still crash. I have social phobia. Any tips for the discussion round? I don't know if I can do this in a larger group. This is, of course, difficult. I understand, and we have, of course, similar situations. You are not required to have your camera turned on for the discussion round. So it's already a lot better than, or it might be a bit better for you than having the discussion round in person in a seminar room. So maybe this is already contributing a bit. The other part is, so of course, there are some things that you cannot work on if they are, there are some things you cannot work on, and other things that you might want to try working on, because the university gives you an environment where you can fail very softly. If you participate in a discussion round and you realize that it doesn't work, you can you don't lose much. Similar for exercises. Let's assume you're unsure about exercises, you participate and then you fail. You fail at university very, very softly. For instance, if you don't meet a deadline, you fail very softly because you can have a second chance, or you can hand in later, or you can take the class again the next semester without losing too much. Later on in your industry career, or generally in your career, this might be more tricky. So I would definitely recommend using this opportunity to practice these things, even if this is an immense challenge for you. It might be valuable to try practicing this, because you might be confronted with similar situations in your later career. And I totally understand that this is a big problem, but what many people, so I know some people that have problems in this direction, and what I found, what helped them a lot is to basically go through the same process that an actor would go through. So they will join any group meetings, any larger groups, playing a role, not being themselves, but playing a role, and this would provide them more of an isolation to the group. So university will give you the opportunity to try around things like with things like that. If it totally doesn't work, so I would expect you to try whether it works. If it doesn't work, we can still you can still get in touch with me after the design discussions if you participated, and then we can figure out whether there's a solution. I see 400 students in SLP. If everyone has to say 3 things and takes 5 seconds to say one thing, that's 6,000. Yes. Yeah. It's absolutely correct. We are not having 400 students in the discussions because a lot of students already stopped participating. So we are expecting more like 200 students. And we will have roughly 10 time slots for discussions. So we organize that it should work, especially for the tutors. It will be in this dimension of, maybe hopefully not 100 hours, but definitely more than it will be like 10 groups with each 1.5 hours, so it would be 15 hours. It's doable. 6,000 seconds is not 100 hours, though, I think. Is it 6,000 seconds? No, 3,600. Is it 100? I'm a bit confused right now. Oh yeah, no, it makes sense. Yeah. So it's, yes, of course, it's 100 hours. No, you're right. I was a bit confused. Right? 3,000. Yes, it's 100 minutes, right? 100 minutes. Yes, 3,600 seconds are 1 hour. So it won't be, so it will be 15 hours in total. So more than you estimated, but you had one unit error in there. For the A3 Abgabegespräch, will you count all questionnaires? Just A3. This counts just A3. Daniel MVP. Okay. Thank you. How many people are there in the discussion round per time slot? I think 20 to 30. We have to arrange that, but more than 30 is not doable. Do we need to sign up for the discussion rounds? Yes, you will find that on your details page in the test system. If you go to your details page, you can sign up for a discussion round already, as far as I know. For the discussion round, is it possible to answer in German? Yes, you can answer in English or in German, and the tutor will adapt to the requests of the group. So if there's no one in the group that prefers English, the discussion round can also be in German. If there's one person at least that prefers English, then the discussion round will be in English, but you can also answer in German always. So we get points from the discussion, not from the number of correct answers in the questionnaire. You get points from the correct answers in the questionnaire, and the points from the discussion will be a factor that will be multiplied onto the points that you got from the questionnaire. So both of them play together. If you participate only a bit in the discussion, you might have a lower factor than if you participate a lot. And then if you have a lot of questions answered correctly, you might get fewer points if you haven't participated as much. Okay. Do we have to contribute on a discussion by our own? Some people are good talkers, but I'm more an introvert. I totally understand this this problem. Again, I would recommend to use the playing field of university as an opportunity to practice, because later on in industry life or in your career, you will face similar situations where you will need to present something, where you need to contribute in a discussion, and this will be crucial for your career. Here you can try this without any hard consequences. If you run into a similar situation, for instance, during application, during interviews at a company where you apply for a job, this can be much more of a problem. If you give a presentation somewhere at a conference to also advertise yourself as a person, this can be more of a problem, and it can block your career chances. So using university as a playing field where you can try this out without severe consequences, it's definitely something that you should invest time on. Just one example, for instance, you see that a lot. You will also find these recommendations. If you are interested in a job, you have found this one job that you really want to have. Something that you will find in a lot of career advice guides is to apply for several positions, similar positions, before this one that you are really interested in. Because this will give you experience. It will give you the opportunity to practice and to fail softly, because you're not interested in these other offers. So if you have maybe 5 offers that you're interested in, also search for 5 offers that you're not interested in, and just go through the process and see how well you do, see where you can improve, see what you can pick up, and that will definitely increase your chances. And using university similarly to improve skills is a very, very good idea. Okay, this sounds really chaotic and unfair. So the discussion rounds, we have moderation in there. So once you said 3 things that were counted, the tutor will ask you to not talk anymore unless before raising your hand virtually, and the tutor basically would then ask you to contribute. Or maybe the tutor will say, okay, first everyone who hasn't said this much yet, and this would be part of the moderation. We're doing this since several years, and I understand that this can be challenging for some students, but at the same time we have discovered that this format makes the knowledge be more memorizable for the students, because you're working on this on your own. Yeah, so we are trying to make this as fair as possible, and if there's any point where you say this was not fair, ideally point us to it directly as quickly as possible, so that we can fix the problems as quickly as possible. Will we be able to see the points we got on the questionnaire before the discussion, so we can judge if it even makes sense to participate in the discussion? Yes. Yeah, wait a second. No, wait, no, actually, now that I think about it, no, you won't be able to see the number of points before the discussion, because we only reveal which answers were correct later on. So you won't be able to see that. But also the distribution of points that we usually see is, yeah, it's a pretty regular Gaussian curve with a broad tail in both directions. So for most students, it's not zero. It's not close to zero. So the average will be a bit above half of the points. Is the discussion round taking place on Discord? How will the tutors identify who said what? The discussion round will take place on Discord, yes, and the tutors will moderate the discussion. So they will either go around and ask person after person, or ask you to virtually raise hands and then pick one person. So they can also schedule things there. So I'm sure that this will work well. We also have done that last semester in Discord already, because we already went completely virtual last semester in that was in late March when we went completely virtual. And so these discussion rounds already have taken place online, and it worked quite well there. The tutors will also tag you if you already said enough. So you will see that visually, that you've said enough and that you should not talk anymore without being asked, and without first raising the hand and then being asked to say something. So the moderation, I'm sure that I'm sure that it's on the one side struggle for some students to participate there who are less extroverted, but I'm also sure that we can do our best to make this as fair and as comfortable for everyone as possible. I would try to ensure that. I will have another chat with the tutors to make sure that we really address the concerns here. And with that, I would like to close the lecture. We again went a bit over time with the Q&A, but we definitely finished the lecture on time today. It's just the Q&A. And there's also now the question hour starting in 10 minutes. So I will also join that. So see you there in 10 minutes. And thank you for all the questions. There's one more. What if several people raise their hand at the same time, first come, first serve? Yes, or the tutors might also schedule who already said how much. They keep track of who said how much, and then they will balance things out between the students so that it becomes fair. Oh, okay, there are more questions in there. How will our Discord identities be associated to our university identity? Not to the university identity. Also, I wouldn't use so if you are not comfortable with using the real name, which I can totally understand, then don't use your real name. What you should use though, so that we can keep track of who said what, is the group number that you have in the SLP test system. This is just a random number, more or less, This doesn't tell anyone who you are, because even the high score list in SLP is completely opt-in, so no one can link this to your real identity if there are privacy concerns. The A3 points are calculated by right answer multiplied with the discussion thing. It is possible to reach 15 points if I only answer the half of the A3 questionnaire, but be great at the discussion. I would expect that the points for the discussion are moving. If you say nothing, like at 0 points. If you say a bit, then maybe 50% of the points. If you say a proper amount, then it should get 90% as the equivalent of a 1. And if you say really more than we expect, so this is the point where we then also will ask you to stay a bit more silent and give others more room to contribute. This is the part where you might get something like 105%, 110%, but more than that, it's not possible. And maybe we should introduce, if people then still talk without being asked to go back down with the points, but that would be a bit too harsh, I guess. Anyway, thanks for being here today in the stream, and see you in 5 minutes in the Discord. Bye.